Okay, so let's take a look at some of these workbook problems. So if you're struggling with this stuff to try and understand it from the lecture videos, start out working through some of the textbook problems, which are a little bit easier, before you kind of dig into these workbook problems. Although ultimately, I think you want to be where these workbook problems are. So let's just take it from the top here. The first problem on page 85 is this as a substrate, and then we're taking sodium hydride and applying it to it. So the first thing you'll notice is that this substrate is much more complicated than any of the ones that I've worked through with you so far. But try not to let that intimidate you. Let's just go case by case, or let's just go like piece by piece, and we'll sort of break this down. So first of all, this leaving group is going to be unfamiliar to you because we haven't learned it. That is a methyl group. That's what MS stands for. And it's not really important what it looks like, but you can just think of it as being similar to like a tosyl group. It's the same thing. It's another type of group you can use. You can do what's called a methylation to a hydroxyl group to make a hydroxyl group from a bad leaving group into a good leaving group. Same kind of thing. So nothing crazy about that. And then we have to kind of look at the other parts of this then. Let's say, what is the substrate itself? So you look at the carbon that the leaving group is attached to, and will we say that's secondary, tertiary, etc.? This is secondary. So we're just when you're counting secondary, tertiary, etc., you're not counting the leaving group as being part of that. The leaving group is, you'll notice I count this and I count that. Those are my carbons that I'm counting towards it being secondary. The leaving group up at the top doesn't actually count towards it being secondary. That's just the thing that leaves. We're only counting things that are carbons that are bound to it. Okay, so it's secondary. So secondary is the hardest one. So of course we're starting on the hardest example possible, unfortunately. So it could go E2, it could go SN2, it could go SN1E1. We don't really know. So that being the case, we want to come over and look at our reagent. So our reagent now, we know, since secondary can go through SN2, we're going to say, like, if we're just starting with the substrate, what does that tell us? We know it could go through SN2, we know it could go through SN1, E1, and we know it could be going through E2. It could be any of them. Secondary supports all of those. So we know that we have to go to the reagent. What is our reagent here? So it's sodium hydride. So remember, I've said this in class before, but I'm going to say it again. The sodium is just like, it's a counterbalancing metal for the charge. It's got a positive charge, which means that the hydrogen is a hydride. Hydride is an extremely strong base. So we're used to dealing with hydrogen as H+. Here we're looking at it where it hasn't lost both its electrons, it's kept them. So it's just a strong base. So sodium hydride, and I think we've been over this in something else, but I'm just going to reiterate it because it's not something we've dealt with a whole lot, is a strong base. So that alone is enough for us to be able to answer this question. So will it go SN1E1? No, because in order for SN1E1 to be competitive, you can't have a strong base or a strong nucleophile. So we know that's not possible. Then we come over and we look at SN2. So SN2 can sometimes be competitive if we have a strong base and a strong nucleophile, but not when it's secondary, because the steric situation slows the SN2 reaction down such that it allows E2 to be the most competitive. So what ends up winning out here it's going to be E2. And so predicting the product of this is actually a little bit more complicated than some of the ones that we went over, because remember, E2 has this stereochemical situation where it has to be anti-periplanar. So that means there's a hydrogen that's jutting out here that we're going to be interested in. And we have all this junk over here. Okay, the only beta hydrogen that we have, let me make sure that I'm correct about this. Yeah, the only beta hydrogen we have is this hydrogen right here. If you come over here and you look at this carbon atom, there are no hydrogens on it. So the only beta hydrogen that we can even pluck off is going to be the one that I've highlighted there. Okay, so we know that we want to get that hydrogen anti-periplanar with the mesylate. So just like we call a tosylated hydroxyl group a tosylate, we're going to call this mesylated group a mesylate. So I want to get the hydrogen anti-periplanar to that mesylate group, which it is not currently in the conformation as it's drawn. So this requires some, visualization. I am going to start by, so I'm just looking at conformational analysis here. I am going to put the mesylate group, there's probably a bunch of ways that you could think about this. Whatever way you do it is fine. So I'm imagining taking and rotating the mesylate group towards me out of my iPad. So as I do that, this big group back here with the methyl group and stuff is going to rotate back behind my iPad screen. And then there's a hydrogen that's not drawn here. That's right there. Again, not a beta hydrogen. That would be an alpha hydrogen. And that's going to rotate now down to being right here. So kind of a difficult rotation to do in your brain. Trying to think if there's an easier way, but that's the only one I can really come up with. What does that do to this? It leaves it there. This is the bond that we're rotating around here. So this bond, that's what I'm referring to when I say this, stays in place. And I'll just redraw this other stuff over here. And so all I'm trying to do is get everything in the same plane. That needs to be in the same plane. So I need to get, in order to get things anti-periplanar, this has to be coplanar with this hydrogen. So the easiest plane to work in is the actual plane of the page. And so that's all I'm really trying to do here. So I rotated the mesylate group, and now I'm going to try and rotate the other side. So I'm going to hold this group over here stationary. And I'm going to take this group over here, and I'm going to rotate that such that I can get the hydrogen into the plane. So to do that, I'm going to rotate this back. So when I'm going to rotate, I'll stick with the blue. I'm going to rotate all of this, and I'm going to leave this other side. I'll put that in red. I'm going to leave this side stationary. And in the first step, I did the opposite. All right, so now my hydrogen is here. This I don't care about. This isn't changing. Okay, so that stayed the same. This is the same. I haven't done anything to that. And now, but I've taken this hydrogen now and I'm rotating it back. So I'm rotating that not 120 degrees, but 60 degrees so I can get it into the plane. And that's sort of a hard rotation to do. The result is that now, as I rotate that back into the page, the ethyl group is going to project out. And the methyl group is just going to stay going out to the back. It's going to be going back into the plane, but it's just going to be rotated up 60 degrees. Okay, so not the easiest rotation to do. And you could try and just do a Newman projection or something if that makes it easier for you to kind of see. That just kind of depends on how you visualize things. All right, so now that we've got everything in the right conformation, however you've done that, whoever you've gotten everything into the correct conformation, whether it's by the way that I did it or by some other method, now we're ready to actually go through and do the E2 reaction. And they're not asking you to draw out the mechanism here, so you don't have to. And you don't have to draw out any of this stuff. Obviously, it's a workbook. We're not going to grade your workbooks, but I think it's informative to do so. So now that I've got everything in the right conformation, I can predict the appropriate stereochemistry here. So everything that is on there we go. Everything that is on the front bonds here are going to be on one side. And everything that's on the back bonds, so this and this, are going to be on the other side. And that gives me my product. Okay. So these can get pretty difficult even once you identify the appropriate mechanism if you have to get it into the right conformation to undergo an E2 reaction. I think this is probably one of the harder, this is a difficult example to start on, but I think this is probably one of the harder cases to deal with in terms of predicting stereochemistry. Needing to get everything anti-periplanar, it can be a little bit of a pain. But if you did well in the conformational analysis work that we did at the beginning of the semester, this stuff shouldn't be super difficult. So another way that you could try and get at this, instead of kind of doing it like I did it, would be to try and do a Newman projection where you look down this bond here, and then once you get everything lined up, you can sort of back things out of that. And I'll leave that as an exercise for you. If you're struggling with this, I would definitely recommend talking to one of the TAs during office hours. Okay, yeah, let's look at the next example now. Okay, so this one I look at, yeah, okay, sodium cyanide, it's a good nucleophile. But the thing that really stands out to me, and the place I almost always start my analysis, trying to be somewhat consistent with my colors here, as I look at the substrate. What is this? Okay, it's, yeah, I don't know, it's primary, but what really stands out to me is that this is sp2. So sp2 hybridized carbons rarely undergo, and as far as we're concerned, well, let's just say rarely. Generally, we're not going to ask you to do substitution or elimination on one of these things, but there is an exception, of course. Rarely undergo substitution, elimination. So if you see one of those, generally speaking, you can just say no reaction. The exception to that is what we've seen when we do our LDA reaction to get an alkyne. So if you have something like this, and you want to make it into an alkyne, remember you do LDA, and you use an excess of it. What's happening there is you're getting an elimination in the first step, and then LDA is such a strong base that you can actually undergo elimination in a second step here. But this is the exception to the rule. Generally speaking, elimination or substitution for that matter, on an sp2 carbon is unusual. Okay, so it can happen, but you have to use a really strong base, and we don't have that up here. We're using sodium cyanide, which is a good nucleophile, so you just don't really see any reaction there. And I would say, just generally speaking, with this singular exception, this is the only case where we would say that this goes through elimination in a second step. If you see something where it's a leaving group like this, and it's attached to an sp2 hybridized carbon like this, then you can just say no reaction and move on with your life. So I guess what I'm saying, for this exam, just assume that anything attached to an sp2 doesn't go through elimination or substitution, even though we do see it in one of the reactions we know. That's the only time that happens. Okay, let's move on to the next example. They really got us with the first example being really hard. And the second one has no reaction. This one's kind of interesting. So we've got some sort of alkyl halide, benzyl halide, and a crappy nucleophile slash base. All right, so this is an interesting one. So it's primary, but it's primary benzylic. So ordinarily, primary benzylic, ordinarily primaries can't go through can't go through SN1E1. Excuse me. They can only go through SN2 or E2. But when it's benzylic, it can go through SN1E1. So primary benzylic or primary allylic is a lot like the secondary substrate in that it can kind of do anything. So you have to go and you have to look to the reagent. So we look to our reagent here. Well, our reagent is a bad nucleophile. It's also a bad base. What does that tell us? Generally, that's going to favor SN1E1 because it's going to make E2 and SN2 not competitive. And that's what we'd see here. So remember that I said SN1 and E1 occur together. That is true, but in order for it to be true, in order for you to actually see the elimination mechanism, you need a beta hydrogen. And you'll notice here, if we come and look at our substrate, there is no beta hydrogen. This is where the beta hydrogens would have to be, and there just aren't any hydrogens on it, so we don't have to worry about that. So we just see SN1, and we just see this single product come out of it. If we had a good nucleophile or a strong base, we would see an SN2 reaction happen there, right? No E2, no elimination reactions because no beta hydrogens. Let's look at the next one. All right, so now we have benzylic. So it's a primary, primary benzylic, which we just looked at. What are we expecting that to go? Well, it could be anything for the same reasons that we discussed. So we come and we look at our reagent. What is our reagent? Bad nucleophile. Let me use the abbreviation here just to save some time. It's a bad nucleophile, and it's a bad base. Okay, so then we know that it's going to go SN1, E1. Again, it's benzylic. There are no beta hydrogens, so all we actually see is the SN1 product that comes out of this. Let's look at the next one. All right, first let's look at our substrate. Let's look at our substrate. What is this? It's going to be secondary. What is secondary going to favor? Well, it's going to pretty much favor anything. We have to go and we have to look at our reagents. So here, what do we have? So remember, potassium, it's just a countercation, excuse me. So we're just looking at the counter anion here. And this is a good nucleophile, a very good nucleophile. But it's not a very good base. We're just going to call it a bad base. It's not a strong base, right? So it's a weak base. Maybe bad is a bad. Bad is not the right. Let's call it a weak base. Weak is a better word to use than bad. Okay, but good nucleophile, weak base. So if it's a weak base, that's going to mean it's not going to be favored for E2. Good nucleophile means it's not going to favor SN1E1. What's it going to be? It's going to be SN2. And so this is a nice example because the substrate actually has some stereochemistry. We're starting out with 100% of one enantiomer. We don't see the racemate here. We just see that whatever this enantiomer is. It's 1. Yeah, so this would be the R enantiomer. So we have 100% R that we're starting out with. We subject it to this nucleophile, and what do we get out of it? We know that we're going to get inversion of the stereochemistry. So I will take, there's a lot of different ways you could do that. What's the most informative? What's the one that makes it most obvious? I'm not really sure. So what I did in my mind's eye here to do this, and again, you don't have to do it this way, is I imagine this coming in and attacking at the front there, and then as it attacks at the front, these groups move back. You don't have to do it that way. You can do it whatever way you want. But yeah, as that departs, I know that the sulfur or whatever is going to attach to the front of the molecule. And the main thing that it's going to do is it's going to push this group that was sticking out. You can see over here now it's in the back of the plane. And now what do we see stereochemically in the product is we don't see any of the other enantiomer. We just see this one. And let me see in my mind. Yeah, so now we see that this is S. So we went from 100% S, sorry, 100% R to 100% S over here. And that's what we expect for SN2. We expect that. So we don't see any of the other enantiomer. You just get 100% inversion. Remember, we call that stereospecific, and of course, it's also stereoselective. Okay. Here's an interesting thing to hold that up against. In the next example, we have the same substrate. So it's secondary. This is secondary, which means it could be anything. That doesn't tell us that much. So we have to look at our reagent. Well, what's our reagent? Our reagent is I'm going to switch over to these terms. Weak, it's a weak nucleophile. And it's also a weak base. So this is going to favor SN1, E1. So this one we actually have beta hydrogen, so we'll see both products. I'm not going to draw the mechanism out for this just because it's this is one of the longer mechanisms. But the products that you would end up with here is the substitution product, which is kind of interesting, is you would end up with this, but you'd also end up with the other enantiomer. So, I don't know, if we were actually taking paper exams, a lot of times you'll write out plus enantiomer. But, what would our enantiomer look like? It would be what you'd get if you just switch out two of the groups. So you'd get that, and then you'd also see the elimination product. And so your elimination products on this would also be kind of a mess. So you would get, so our beta hydrogens are here, but we also have beta hydrogens that are right there. Actually, I guess it's not so messy. So your elimination products here, you would favor the most substituted alkene. So you wouldn't favor, let me see if we can do, nope. These beta hydrogens over here wouldn't react because that would lead to the less thermodynamically stable product. And we would favor the trans alkene. So you would see this. Yeah, so we get that out of it. And then, maybe some smorgasbord of minor products, the cis alkene, the less substituted alkene, etc. But these would be your major products, which is typically all we're asking for on an exam. So this goes through SN1, E1. So same substrate, but just different reagent and just different outcome altogether mechanistically. Okay, next problem in the book is this. I'm glad we could revisit this. Here we have this, and we've got sodium hydride. The thing that should stand out to you immediately is that we have an sp2 hybridized carbon there, and we're just going to say no reaction. So don't have to worry much about that. Next example. We're kind of speed running this workbook problems. All right, so we've got, that's our substrate, and then we're looking at doing this in 1, 2, 3, 4 butanol. Yeah, what's going to be our reaction here? So the first thing we start out at is we look at our substrate here as primary. Nope. So we're primary, so that's generally going to favor SN2. But then we look at our reagent, which is this butanol thing. And this is a weak nucleophile. And a weak base. Yeah, so what's going to happen here? Realistically, on any kind of practical time scale, you're probably going to see no reaction. So if you have a bad nucleophile and a primary substrate, so a weak nucleophile and primary substrates generally are going to favor SN2, and if they don't favor SN2, they'll favor E2. But since we have a weak base here, we can't get any E2, so we're just looking at an SN2 reaction. And so maybe over a long time period, you'll start to get some slow SN2 here, but more realistically, you just get no reaction. And that is going to be exacerbated by what's called beta branching over here. So even though you've got a primary carbon here, you have a lot of branching on the carbon that is beta, and that also constrains the access to the antibonding orbital or whatever, right? So it increases steric hindrance, even though it doesn't follow sort of I don't know, it doesn't follow like just kind of what you just bluntly learn, which is like primary favors SN2. Yeah, it favors SN2, but what really favors SN2 is a place where you have no steric hindrance. So here your steric hindrance is on the beta carbon, so it additionally slows down that reaction. But the reaction was kind of screwed from the beginning, so it doesn't really matter. So this is a no reaction or slow reaction. For us, I would just call that no reaction. All right, let's look at the next one. With this one we have an alkene, and we're treating it with sodium cyanide. So let's just start out with our substrate. It's primary, but it's also allylic. Remember alleles, that's when you have, the allylic position is right here. So I have a carbon that's in the allylic position, and then the bromine that's attached to it is obviously also allylic. And so, yeah, so primary allylic, those can do anything, so we have to go and look at our reagent. So let's consider what sodium cyanide is. This is let's just call it cyanide. Get rid of the sodium, right? It's just to counterbalance the charge. This is a very good nucleophile. Really, I should be keep saying good and bad. Strong, weak, but it's a weak base. So when we say weak and strong bases, especially for these reactions, we're generally calling anything that is a weaker base than anything that's not, anything hydroxide and stronger is a strong base, and anything weak, anything else is considered a weak base, right? So if we're talking in terms of pKa, we're looking at things where the conjugate acid has a pKa of less than 14. Okay, so weak base, not going to be E2. Primary allylic means that it could be SN1E1, but we've got a strong nucleophile, so SN2 is going to win this match. There's no stereochemistry to worry about. This is just a straightforward swap one group for the other. All right, next example. So here we have, what's going on? We've got a phenyl group. And then we have this tosylate group over here as our leaving group. And then we're in potassium iodide. So this is where I've highlighted in purple here. That's our actual substrate. And note that it's primary, but it's not benzylic. So the benzylic position is right here. In order for it to be benzylic, it has to be directly attached to the sp2 hybridized carbon. In this case, that carbon is not directly attached to it, right? It's going to be 2 carbons removed, so it's just a normal primary substrate. All right, so normal primary, so that's going to favor SN2. The exception is if you have like a really strong bulky base like terbutoxide, which we do not here. We look at our reagent, so I'm dropping the potassium, and that is a strong nucleophile, but a weak base. Okay, pretty straightforward one. I wish they'd have started us here in the workbook. Okay, weak base means it's not going to be very good at E2. We know it favors SN2 already. We've got a strong nucleophile there. Yeah, this is a straightforward case of SN2. And we know that SN2 is going to invert the stereochemistry. There's a terrible, there we go. It's going to inverse the stereochemistry there. So here it's not drawn, but there's a hydrogen on the front bond. Now we see it's on the back bond, and that's just the result of that one. Yeah, that one's reasonably straightforward. That's probably the most straightforward reaction we've looked at so far from the workbook. Okay, man, how many problems do we have in this workbook? So many problems in here. I guess one good thing is, since they clearly don't put them in order of difficulty, they don't go easy to hard like most things do. It's just kind of problems. I'm not biasing things to where I'm just working out the really easy problems here for you guys. We have a whole bunch of hard ones, even if I don't get through every single one, which I'm not sure I will because there's several more pages of these. Okay. Let's look at this one then. So that's our carbon that's going to be considered for our substrate. It is not primary, as I've written. It has one carbon that's part of this phenyl ring. It's got another carbon here. So this is going to be a secondary carbon, which we know is not super helpful. That doesn't favor or disfavor anything. We have to come and we have to look at our reagent. What is our reagent? It's not really sodium amide. It's NH2 minus. And that is a strong nucleophile. It's also a strong base. Okay. So remember for secondary, where you've got this case where the sterics are such that it slows the SN2 reaction down a little bit. So as my nucleophile, if my nucleophile is trying to come in to sort of gain access to this antibonding orbital right here, it's going to be blocked by the steric hindrance of all this crap around it. That's what secondary does for the SN2 reaction. So SN2 is slowed down, and if there's a strong base present, which there is here, that's going to favor E2. Okay, so now we've got a situation where we have stereochemistry to worry about. So this is the worst, or the hardest stereochemical situation to deal with. So we have to get things anti-periplanar. So the bromine, I'm going to draw the conformation for that down here. The bromine is already in the plane, so I'm just going to leave that there. I'll draw this hydrogen out front. Yeah, there's only, in terms of beta hydrogens, there's only this beta hydrogen, because this other group is a phenyl group, and so phenyl groups don't have any hydrogens that are going to participate in this reaction. So all we're trying to do is get this hydrogen here. So I'm trying to go fast through these things, and I'm making me a little messier than I usually am. All right, what I'm trying to do is I'm trying to get this hydrogen here, that's on this front bond, into the same plane as that bromine. All right, so how do I want to do that? I would just take and put the hydrogen in the right place and then figure out where the hell everything else goes. So if I'm going to rotate, I'm going to keep the bromine and phenyl and stuff where it is because that's where I want it to be ultimately. I'm just going to rotate the hydrogen I'm just going to imagine like grabbing it and I'm just steering it back into the page to put it in the plane. So I'm going to rotate it 60 degrees to the back. What that's going to do is it's going to push the ethyl group 60 degrees to the front, and the methyl group is going to go 60 degrees down. That gets, that puts things syn periplanar, which is not what I wanted to do. So syn periplanar is when they're on the same side. I want them to be anti-periplanar. So I'm going to have to do another little operation here. What do I want to do? Let's see. I will just take and put the bromide down. So when I rotate this bromide down, what I'm imagining doing is, let's see. I'm imagining, let me try and put a little bit of perspective on my arrows so they make some sense. I'm imagining pushing it backwards into the plane. So I'm rotating it 180 degrees around. And it doesn't matter which way you rotate it, but that's what we're doing. When I rotate it 180 degrees down, everything gets transposed 180 degrees. What do I mean by transposed 180 degrees? Well, if I look at this phenyl group where it is here, if I were to transpose it, all I'm really doing is moving it 180 degrees, so it's just kind of moving straight through that plane. So remember, 180 degrees just kind of flips everything around. 360 would actually return you to the original position. It'd be like an identity operation. But 180 degree rotation just takes you from one position and sort of puts you on the opposite side. So I've just sort of moved the phenyl group to the opposite side. And you can see the same thing for the hydrogen here. I've just sort of moved it straight through the plane to push it towards the back. Not sure I'm doing a great job of explaining that, but that's kind of how I'm thinking about it. Hopefully you built up some nice tricks of your own when we went through the conformational analysis stuff. If you didn't, yeah, if you didn't, I would say you want to return back to that because obviously you're going to need that. But I would start by just being like, well, I don't understand the stereochemistry stuff because I sucked at the conformational stuff, or I forgot it, whatever. I mean, suck is kind of harsh. But you can come back to that. That's not the major thing that you're trying to learn here. What we're trying to learn is just what happens, like predicting the actual reaction here. So if you can predict this as E2, you're doing pretty well. All right, but now I've got these things. Now I've got these things anti-periplanar to one another. And that allows me to say, well, that's on the front bond, that's on the front bond, this is on the back bond, this is on the back bond. So when the NH2 minus comes in and kicks those off, sorry, I'm trying to make you guys nauseous, or nauseated, excuse me. Now the phenyl group is going to be on the same side, and the hydrogen and the methyl group will be on the same side. Okay. And that is how you work these. So the E2 is like definitely the worst in terms of stereochemical consequences. So once you predict it, you're like, okay, now I've got to do this other stuff. So if you got stereochemistry to worry about, it kind of makes things a little bit rough. If you started with different stereochemistry in the reactants over here, you would end up with some different stereochemistry in the products, and that's what we call stereospecific. Stereospecific means that the stereochemistry of the product depends on the stereochemistry of the reactant or the substrate. Okay, let's see, where are we? Oh, these examples actually, these next two are kind of rough, but I'll work through them. So you'll notice that my analysis every single time is the same, and obviously I'm going pretty fast because I'm trying to get through a bunch of these, so you guys both have the solutions and some blueprint to work on stuff with. At the very least, it'll give you a leg to stand on when you're asking questions during office hours. But generally the way that I'm solving these problems is the same each time. I look at the substrate, and then I look at the reagent, and then I make some sort of decision about what it is. And then if I have some stereochemical situation, so this is LDA, which I do here, I worry about that last. So LDA looks like this. So LDA is a strong base, and it's sort of like the tert butoxide equivalent for amines, for when you're looking at these types of bases. It's got these big bulky groups on the side, so it generally disfavors any kind of SN2 reaction. But let's come over here and kind of do like we've been doing. We'll find out what our substrate is, and we'll go from there. Ooh, how bad does this thing get? All right, this might be an interesting one to work through. We're doing time. Oh yeah, we've been at this for a while, 45 minutes now. Yeah, so what is this? This is a tertiary substrate. Tertiary. I think we're okay. I was going to say, so one of the things you have to watch out with for SN1 and E1 is that you can get, because you're forming a carbocation, you can go through carbocation rearrangements. Just like we did with alkenes, anytime you form a carbocation, if it can rearrange to something more stable, it will. So keep an eye out for that. I don't think it's an issue here, though. All right, so it's tertiary, so generally that's going to favor SN1. E1, except if we have a strong base, which we do. So we've got our base, which is I wouldn't say it's a weak nucleophile necessarily. Yeah, let's call it a weak nucleophile. It's not a weak nucleophile in the thermodynamic sense. It's just kinetically kind of slow because it's bulky. But it's a strong base more than anything. Let's just say, let's call it sterically hindered strong base. And then in your mind, hopefully sterically hindered is coming into, like when you hear those words, you should immediately think of an SN2 reaction not being favored. All right, but so we've got a sterically hindered strong base. Those are generally going to favor E2. So now we're back to this thing where we have to figure out the right conformation and all this kind of crap. So yeah, SN1E1 wasn't even a concern here. So what I was saying about carbocations isn't even relevant. Now we just need to worry about what products we're going to get here. So our beta hydrogen that we're interested in is this. There are no beta hydrogens on the tert-butyl group. And so we're just trying to get everything in the right conformation so that our stereochemistry is correct. I keep thinking there's got to be like a better trick than the one that I'm using. But this is the only one I can think of, is to actually just rotate things around. So I'm just going to do one, this is what I was trying to do in the last one, but I'm going to try again. Just do one single rotation on both sides and do this kind of in my head, just for the sake of saving time. So I'm rotating this hydrogen in my mind. I'm kind of rotating it back. I'm trying to show with this arrow here is that it's going back into the iPad screen. So I'm rotating it back 60 degrees, and the result of that is the isopropyl group is going to stick out, and the methyl group is going to be right there. So it's still in the back of the plane, it's just moved up 60 degrees. And then, let's see, on the other side I want to get the bromine here. And so to do that, it's been a little while since I've taken an art class, maybe 15 years, so bear with me here. I'm trying to show some perspective on the arrows. Okay, so now I'm trying to show that bromine coming towards us. That's what I'm trying to show here by this getting wider at the back and then getting thinner at the front. That's coming towards, kind of out of the plane of the screen. And so what's going to happen is everything else is going to move 60 degrees. The phenyl group is going to be 60 degrees down, and the tert-butyl group is going to move 60 degrees back. And now I've got everything anti-periplanar, which is what I wanted. So ultimately we wanted to get this and this in the same plane, and that's what I've done here. And if I got this wrong or you have questions, feel free to beat on me in the comments. Yeah, so now I've got it in the right spot, so now I just want to take my base. And again, the question isn't asking to draw this out, I'm just doing this because I think it's informative. And our stereochemistry is such that everything on the front bonds, which is this, and everything on the back bonds, this and this, will still be on the same sides in our product. And that's what we get out of it. Let's see what our next question is. So yeah, so this is, I see. So this next question is kind of neat. So this kind of demonstrates exactly what stereospecificity is. So I'm going to see if I can squeeze it in right here, put it all on the same screen. Everything is the same in this next question. So we have two chiral centers in this molecule. The first one that I'm drawing right now, this one. And then we have another chiral center right here. And what they've done in the workbook here is they have switched to substituents on this second chiral center. So if you look at this one and you look at this one, you'll notice that the substituents has switched. Everything else is the same though. But because this reaction is stereospecific, which means that the stereochemistry of the product depends on the stereochemistry of the substrate, now we've changed the stereochemical outcome here. The question is, how will it change? So you can go through and you can put it in the antiperiplanar position again, conformation, excuse me, to see what you get. But I think we can kind of deduce that what we've switched, since this is the switch, right, is on this chiral center. So these are the groups that we've changed if we're kind of comparing across here. So if I've switched up two of the groups, what I'm anticipating, I'm trying to check this in my mind right now. Yeah, what I'm anticipating is that we're just going to see a swap of two groups on the stereo center in the product. I think that's correct. So for you guys, you might want to go through and do this just for practice of getting in an antiperiplanar, but if you can understand this rationale, that's also very good. All that I'm saying is, since I know that the reaction is stereospecific, and I've switched the two groups on this chiral center, I'm expecting them to just get swapped in the product. And I think, if I'm doing this correctly in my mind, that's exactly what you see. Because now when you line up everything for it to be antiperiplanar, I might as well just draw it out. Now when you line everything up to be antiperiplanar, you'll note that the isopropyl group is now on the back bond, and nothing has changed on the other side. So everything is the same as it looks up at this top example up here, but because I've changed the chirality, or because I've changed the configuration, I guess I should say, of the chiral center, now the isopropyl group is on the back bond instead of the front. And so when I actually do the elimination, the isopropyl and tertbutyl are on the same side, and the phenyl group and the methyl group are on the same side. Okay, so we've changed the stereochemistry of the product because we've changed the stereochemistry of the substrate, even though they're both the same compound aside from stereochemistry. So it's a great example of how the stereochemistry of the substrate affects the stereochemistry of the product for E2 mechanisms. So those are a very good set of examples to work on. Okay. Also, those are two of the, any of the ones that involve E2 and predicting the stereochemistry of the product are going to be some of the more challenging ones. And it looks like they give us a nice, easy one as the next one, which I am grateful for. So here we've got tertiary substrate, which we know is generally going to favor SN1, but we still have to look at our reagent. What is our reagent? It is both a weak nucleophile and a weak base. Yeah, so I think this is a very clear example of SN1E1. There's really nothing else it could be. So if this was a strong nucleophile or a strong base, we might see, well, if it was a strong base, we would see E2. Even with a strong nucleophile, this would still go SN1E1. And so what do we get out of this? Nothing really complicated about our substrate. There's no stereochemistry or anything. We just get, I think I even worked something really similar in the products. I mean, in my lecture or whatever. Yeah, we just get these two products out. Okay, so I like these problems they're giving us because they're just taking and they're kind of, and this is how I like to kind of learn in general, is I take whatever example I understand and then I just screw with that example until I come to a place where I don't understand it. And so we're using the same substrate now, but we're taking methoxide and we're going to see what that does. So we've got a tertiary, generally favors SN1 and E1, but And in the example, they have sodium methoxide. I've just already written it as the anion. We have something that is a strong nucleophile, but it's also a strong base. Okay? So, strong nucleophile will generally favor SN2, but not on a tertiary substrate. We know that that can't happen. And so the real thing that we want to pay attention to here is that we have a strong base. So strong base favors E2 enough that SN2 is too slow, and so we end up getting the elimination product. So you'll see here we're going through E2, but there's no like really complex analysis that I'm having to do because I don't have any stereochemistry to worry about. It's just straight up an alkene. There's nothing to really have to like wring my hands over. So it's not always a mess when it's E2, but it can be kind of messy. I guess we'll keep going with these. How are we doing on time here? Oh yeah, I'm getting on to an hour. Yeah, whatever. I'll just keep working them. Maybe there's a way for me to put bookmarks or something on the YouTube video. I'm worried if I stop, I won't want to come back to keep going on these. Not that I'm not enjoying myself. I actually kind of do enjoy this. Just not as much as playing with my kids. So, all right. Yeah, what's going on in this one? Here we've got, let's take a look. We've got a primary. Nothing weird about it. It's not allylic, it's not benzylic. And then if we look at our reagent, it is a weak nucleophile. And it's also a weak base. So weak nucleophile, weak base, that's generally your cue that you're going to have SN1E1. That's what I'm thinking. I'm like, oh, okay, probably SN1E1. But when we come back up here, we see that this is primary. And so we know that SN1E1 can't happen with primary because primary carbocations are too high in energy. Yeah, so what happens here, it's probably a slow SN2 is how some books would call it. I just say with no reaction. You know, so slow SN2 means, yeah, you've got some reaction, but are you going to set up a reaction that takes a month on an industrial scale to try and get a product out? No, not really. So practically speaking, is this reaction happening? You know, no. You know, we're going to call that no reaction. I think that's fine. All right, let's look at our next example. So here they've gone ahead and drawn out lithium LDA or whatever, lithium diisopropyl amide. And they put the lithium nestled up next to it, which might look funny to you, I don't know. Yeah, what's going to be our product here? So we've got secondary, that doesn't tell me much, could be anything. Could be E2, could be SN1, I don't know. But when I look at LDA, this is a, I'm just gonna call this a weak nucleophile because it's sterically bulky, so I think that's fine. I think that's the appropriate way to say it. It's not a weak base though. I guess the only reason I was hesitant to call it a weak nucleophile is because we do say that all strong bases are strong nucleophiles. So it has nucleophilicity here, but you've kind of tuned that down a good bit with the sterics. But mostly this thing is a strong base. Secondary, strong base, always going to go through E2. Nothing interesting stereochemical here. It's just going to form an alkene. That one's done. I would say if these problems are biased in one direction, it seems like they're getting easier. Although who knows what lies ahead. Okay. So here our substrate is methyl. So methyl is even like less sterically hindered than primary, so heavily favors SN2. Really, it can only undergo SN2 if it's going to undergo anything. Right, there's no beta hydrogen, so it can't go through E2. So then we look at our reagent, and this is the first time we've seen one of these amine reagents. So what we've got here is trimethylamine. So trimethylamine is sterically bulky, moderate nucleophile. If we had beta hydrogens, I might think it could go through some E2. I'd probably call it E2. But because it's a methyl and there are no beta hydrogens, I'm going to go ahead and say that this goes through SN2. And this kind of gets at the problem of what happened in what I talked about in this last problem. So I call this a weak nucleophile. And if I was sticking to that, I might call that a weak nucleophile too, because it's very sterically hindered, etc. But you can see it's still a strong enough nucleophile that it'll react here, right? So it's still a stronger nucleophile than, say, like water or something. So I don't know what the nomenclature is. I mean, it doesn't really matter how we define it, as long as you kind of understand what's going on underneath that, right? So if you have something where you have, like, let's take a look at I'm going to deviate a minute from the workbook problems here. Let's say you look at that last problem where I called it a weak nucleophile, which I'm kind of regretting at this point. But if I were to change it up, let's say, to this, what's going to happen here? Well, yeah, okay, SN2 is slowed way down because of steric hindrance, but it's still fast enough that I'm going to see this weird reaction where I'm actually going to alkylate the LDA, this would be an unusual thing to actually want to do in the lab. So you can still see LDA behaving as a nucleophile, but it's only in this very specific situation where you have a methyl substrate. And as we'll see when we get to the chapter on ethers, you can use this kind of strategy to make ethers from like terbutoxide or something. I just want to draw that comparison to something like if I take this and put it in water. I would call this no reaction. Other books call it slow SN2, but it's much, much slower than if you react it with something like LDA or terbutoxide or something. So when I say weak nucleophile, it's probably not the best definition to use. It's just, I think part of the challenge of teaching this course is that there's like a million exceptions in organic chemistry. Obviously, that's part of the challenge of learning it as well. But, okay. God, there's still 2 more pages of problems. Let me pick out some choice ones here. I'll pick out some of the weirder ones. So the next problem is pretty straightforward. What about this one? For one, this is a big old ring. Usually we're dealing with like 6-membered rings. Here we've got this 1, 2, 3, 4, 5, 6, 7, 8. We've got an octagon, octane, if you will. Tosyl group there, so this is secondary. And then we're subjecting it to a carboxylate. Yeah, so this one is, the more like on the border you get in terms of reactivity, the harder they are to call. So secondary, yeah, is this going to go through SN2, E2? We don't really know, right? That's part of the challenge of it. And then we look at this thing and it's like, it's a moderate nucleophile. It's a weak base. What's going to happen here? Yeah, this is probably going to go through SN2. And where am I getting that from? Well, my thinking is secondary, yeah, that doesn't help me much. But when I come down and I know it can go through SN2, E1, SN1, etc. If my nucleophile here, like if I had used the actual acid, So this isn't what they give me, but if that's what they had given me, then it would very clearly go through SN1E1, because that's a bad nucleophile. But they didn't give me that. They gave me this, which is a moderate nucleophile. And remember that SN1E1, it's like the weakest runner in the race, right? Everybody else in the race has to be like totally incapacitated in order for it to win. And so here it's like, yeah, the SN2 reaction is probably not going to be super fast because you don't have a strong nucleophile, but it's still going to be faster than the SN1E1. And that's going to give me SN2 substitution here, right? So the only way SN1E1 wins is if everybody else in the race is hobbled by the substrate being really sterically bulky and the reagent being either like a super weak nucleophile and a super weak base. It's the only time you really see SN1 and E1 win. Unless the substrate has some special, I don't know, if it's like allylic or benzylic and it has no beta hydrogens and stuff, maybe you start to see some weird stuff. But generally speaking, SN1E1 just doesn't really happen unless everything is kind of tuned down reactivity-wise. Let's see. I think the last one, and this one is not really that interesting, but it might catch you off guard. It illustrates some of the things I talked about in some of the other questions, or maybe it's similar to them. I don't actually remember. I've done so many problems now, I've kind of forgotten where we started, but so here they're giving you ethoxide. And this actually, so this is getting into our strategy that we use to make ethers. Yeah, what do we have here? We have a primary, but it's also benzylic. And then our reagent itself, yeah, I guess this one's not super interesting, but our reagent itself is both a strong nucleophile and it's a strong base. All right. So we don't have to worry about E2 here. I think that's kind of what my main lesson was going to be. Generally speaking, if you have primary and you have a strong nucleophile, even if it's a strong base, you're going to see SN2. So if you're just trying to predict what this reaction is going to go as, that's easy to do. That's what it's going to look like. But even if you tried to do this reaction, let's say I took this and now I'm going to change things up. So again, this is just me making up examples now. Even if I tried to change this up, let's say, and force it like I've done another one. So I take this and let's say I use terbutoxide. Big, strong, non-nucleophilic base. Am I going to get E2 elimination here? The answer is still no, but the reason for that is that there are no beta hydrogens. If there were beta hydrogens here, for example, if I was using a different substrate, let's say I just put an extra carbon atom in, so now I've got a beta hydrogen there. Yeah, that will go through E2 elimination with terbutoxide. No problem. But here, there is no E2 possibility because you don't have any beta hydrogens. So what ends up happening is that even though you've tried to gear things towards E2, or even if you wanted to gear, even things are kind of geared away. I guess what I would say is even though things are kind of geared away from SN2, it's still the only plausible reaction path forward. And this ties in well with what I was saying before, where it's not like terbutoxide is really a weak nucleophile in the same sense that like water is a weak nucleophile. It just heavily favors E2. But you can create situations like this where you just can't even get E2. Wow, that is really off. Probably a good indication that I do need to stop working problems when I'm drawing stuff like that. There we go. I kind of lost my train of thought. Yeah, I think what I was saying was, even when you've got things geared kind of away from SN2, and you're using a strong sterically hindered base, if you don't have any beta hydrogens, you can't get E2 elimination. And so this is one of the strategies that we'll learn about in the ether chapter. The rest of the chapters get progressively easier once you, I think at least. Easier in terms of mechanism, harder in terms of synthesis because you learn more reactions. But this is a way to make ethers. You can do this SN2 chemistry where you just sort of eliminate the even possibility of having an elimination reaction happening. And now I've got kind of this ether there. So yeah, hopefully this kind of speed session of just solving workbook problems is helpful. Obviously I go through these pretty quick. You probably want to slow this down. I don't know if I'll be able to put bookmarks into the YouTube video. There's probably a way to do that, but I'm trying to spend as much time as I can just making content. But yeah, you probably want to slow this down. Take your time with these problems. If there's stuff you don't understand, obviously you want to go back and kind of beat that to death. The main thing that the one thing I like about this workbook is that they don't have solutions, and I'm giving you a lot of solutions here. Don't confuse yourself into believing that because you're following what I'm saying that you actually understand what's going on. Okay? So yeah, obviously I'm working these problems super fast because I have a PhD in chemistry and have taught this course a bunch of times. But when I first started out on this stuff, yeah, it took me time to kind of think through this. And I think it's really important that you spend time thinking through this too. So there's still some problems left in there where you don't have the answers. I encourage you to work through those. But this is at least 2/3, if not 3/4 of the problems in the book. Yep, if you've stuck through past the hour here, hour and 10 minutes on this video and actually getting this stuff, congratulations.